Hello everyone, today I'm going to share two exercises related to topology. Let's start with the first one. Let S be a dense subset of topology space. X and tau prove that for every open site U of X, the closure of the intersection of X and U equal to the closure of U. To prove that this equality holds on, we need to show that the closure of the intersection S and U is contained within the closure of U and the vice versa. Let's break it down step by step. First, let's prove that the closure of the intersection S and U is contained within the closure of U. Since S is the subset of X and U is a subset of X, both being open sites, and their intersection is also within U. According to the closure of A is the intersection of all of closed sites containing A. This one. We can inform that if A is a subset of B, then any closed site that contain B must also contain A. Therefore, the collection of closed sites containing B is a subset of those containing A. Since the closure of A is the intersection of all closed sites containing A, and every closed site containing B also contains A. The intersection defining the closure of B is taken over a smaller or equal collection of closed compared to the close of A. So, the closure of A is contained in the closure of B. Now, if we let A be the subset of S and U, B be U, so we can have the closure of the intersection S and U is contained within the closure of U. Next, let's prove that the closure of U is contained in the closure of the intersection S and U. So, if X is in the closure of U, we can have x is in U or x is a limited point of U. So let's consider two cases. For cases 1, x is in U. Since U is an open set, so any neighborhood of x, we can see V, it is also contained in U. Since S is dense, so the intersection of S with any open set is not empty. So we can have S, the intersection of S, V, and U is not empty if X in S, the intersection of S and U, we can have X is in the closure of S and U. So the closure of U is contained within the intersection, the closure of the intersection of S and U. If X is not in S and U, since the intersection of S and the V and U equal to including X is not empty. So X is a limit point of S, the intersection of S and U. So S is in the closure of the intersection of S and U. So the closure of U is contained within S, the intersection of X and U. And then cases 2. X is a limit point of U. According to the definition of limit points, for any open site, X in W, the intersection of W and U excluding X is not empty, and this one, it is open set. Since S is dense, we can have the intersection of S and this one is not empty. So the intersection of this one equal to is not empty. According to the definition of limit points, we can know X is a limit point of the intersection of S and U. So X is intersection and X is in the closure of the intersection S and U. So we can have the limit points of U is contained within the closure of the intersection of S and U. So we can note the closure of U is also contained within the closure of the intersection S and U. Okay, the next question is let m and c be non-zero real numbers and x the subspace of R sequence given by x equal to xy and y equal to mx plus c. Prove that x is homomorphic to R. We need to prove four things. So first, let's prove that the function of f is 1 to 1 is 1 to 1. 1 to show. Suppose ft equal to ftr. By substituting, we found that mc equal to, so we know t equal to tr. So f is 1 to 1. Okay. Second, let's prove that f is onto for any point x and y in x. According to the definition of x, we have y equal to mx plus c. We have x equal to this one. So f is onto. Third, we need to show that for any open site V in tau, if V is also in tau 1, we can break the map into two parts. Let ft equal to t mt plus c equal to f1 t f2 t. Since both f1 and f2 are continuous, so we can have f is also continuous. So f u is open site in R. Finally, we need to prove that the inverse function is also continuous. Here, we will use definition of continuum mapping. Let x tau and y tau 1 be topological space and f a function from x into y. Then, f is said to be continuous mapping if for each u in tau 1, the inverse of function f u is in tau. So, since we have already proved in the third part that f is continuous, it follows that the inverse function of fu, we have for each, for each u in tau 1. U in tau 1, the inverse of function of fu is also in tau. So x is homomorphic to R. Okay, thank you for your listening.